Hello, great friends. I hope you are doing great. And IBM is here to bring you another episode of Deformation of Solids. Multiple choice questions, AS Physics 9702. This is paper 1. And this is, I think, episode 3 or part 3 of Deformation of Solids. I'm not sure if it is the last part, but it is part 3. So without wasting time, I want to take you to the document and we start solving part 3 from where we stopped in part 2. I think in part 2 we stopped on page 40 and now we move to page 41. Do not hesitate to download these documents. They are free. Learning is free, completely free. So you can download, print, and try to follow in a hard copy rather than following on a soft copy. But you can still follow this in soft copy as long as you understand the concept. All you need to do is just to circle the correct answer just for reference. In the future, when you are trying to revise, you know the answer, you just try to arrive at the correct answer. So without wasting time, let's start on page 41. The Young modulus of steel is determined using a length of steel wire and is found to have value E. Another experiment is carried out using a wire of the same steel. That means the Young modulus is the same, but of half the length, and half the diameter. Which value is obtained for the Young modulus in the second experiment? If the wire is of the same steel, it means the Young modulus is still the same, so the answer is E. These are just to confuse you, to keep you off track. But if it is the same material, the Young modulus will be the same, irrespective of either half the length or half the diameter, the Young modulus will be the same. The graph shows the variation with the stress of the strain of a material as it is extended elastically. Why is the strain energy per unit volume of the material not the area under the graph? Why is the strain energy per unit volume of the material not the area under the graph? So notice that here the area under the graph will be a half strain times stress. And the question is why is the strain energy per unit volume of the material not the area under the graph? So if we try to establish the area under the graph is going to be with the x-axis where we have the stress, and this would give us a half times the strain, which is original length or extension over original length, then times the stress, which is going to be force over the cross-sectional area, which is going to be A. So the question is why is the strain energy per unit volume not the area under the graph? The strain per unit volume will only be the area under the graph if and only if this is strain and the other one is stress, because area under the graph is only going to be equal to the elastic potential energy if a half F times E, where E must be the x-axis. This is going to be the area with the x-axis, with the extension axis. And yet the extension is on the vertical because strain is extension of original length, so the extension is on the vertical. Therefore, the axes are the wrong way around. So the axes are the wrong way around. It would be, of course, from algebra you may see that it is direct, but now note that if you manipulate this, you get a half Fe times 1 over volume. Yes, but now this is only strain energy if the F is on the vertical axis and the extension is on the x-axis. But if the E extension is on the vertical and the F is on the horizontal, then it is the wrong area. Therefore, the answer is going to be A. The wire has a final length 6 meters after undergoing a strain of 200%. That means the strain is 200 divided by 100, which is 2. The strain is 200, is 2. What is the original length of the wire? So we know that strain is going to be extension over original length. So the original length is going to be equal to, because the wire has a final length of 6 meters. So we notice that extension is going to be the original length minus, the final length minus the original length. So we want to find the original length. So I will simply say strain, which is 2, is going to be equal to, by the way, this is over L naught, so it is going to be equal to the final length, which is 6, minus the original length, L naught, divided by L naught. So it means twice L naught is equal to 6 minus L naught. So it means 3 L naught is equal to 6, which makes L naught to be equal to 2 meters. So this is simple algebra. Epsilon, the strain is 200%, which is just 2. So 2 is going to be 6 minus original length over L naught. So our answer is going to be 2 meters. Which statement about elastic and plastic deformation is correct? Elastic deformation and plastic deformation are proportional to the force. That is not true. Elastic deformation and plastic deformation cause no change in volume. Plastic causes change in volume. Elastic deformation causes heating. That is not true. It is plastic deformation that could cause heating. Elastic deformation is reversible. That means it can be taken back. Plastic deformation is not. So the answer is going to be D. Elastic, the material can go back to its original length. Plastic, it cannot. What is meant by ultimate tensile stress of a ductile material? When we talk about the ultimate tensile stress, we refer to the maximum stress that a material can support before it breaks or without breaking. Therefore, our answer is going to be C. The maximum stress that a material can withstand or it can support without breaking, that is the ultimate tensile stress, which in calculation normally represented as UTS, ultimate tensile stress. The Young modulus of a metal may be determined from the ratio stress over strain when the metal is stretched elastically. This can be done by making measurements when loads are added to the wire. Which measurements are needed to calculate the stress and strain of the wire in such an experiment? So for stress, we know that stress is normally written as sigma, is force over area, which can be 4F over pi d squared, because area is pi d squared over 4, so the 4 has gone up. So which measurements? For stress, we might need the diameter of the wire, and find the force. The force is going to be equal to the weight, which is going to be mg, so we may need the mass. So for stress, we need the diameter and the mass. So initial and final position, these ones are going to help us to find the strain. Wire's original length, we don't need the wire's original length to find the stress, so this is also wrong. So our answer remains B. Diameter, mass. For strain, remember strain is extension over original length. Extension over original length, L naught. So it means our answer is going to be B. A copper wire of length 3.6 meters and diameter 1.22 millimeters is stretched elastically by a force of 37. The Young modulus is 1.17 times 10 power 11 pascals. Which extension is caused? So we know that Young modulus is going to be 4 times F over pi d squared. That is force over area, but area is pi d squared over 4. Then multiplied by original length L naught over extension E. That is the reciprocal of strain, because strain is equal to extension over original length. So we get the reciprocal. So I make E the subject here. I'll make E the subject. So extension is going to be 4 times F, which is 37. Original length is 3.6 divided by pi. Our diameter is 1.22 times 10 power negative 3, but this should be squared. That should be squared, then times Young modulus. I've made E the subject in this expression here. So E goes this side and Young modulus comes in the denominator. So times 1.17 times 10 power 11. So for my calculator, I have 4 times 3, 7 times 3.6 divided by, we have pi 1.22 exponent negative 3, that is the diameter, but is squared. Then 1.17 exponent 11, that is the Young modulus. So I close that bracket. So this is giving me 9.7 times 10 power negative 4 in meters. 9.7 times 10 power negative 4 in meters. The answers are in millimeters, so I'll multiply this by 1,000, which is 0.97. So the answer is going to be C. The stress strain graphs for three different materials are shown not drawn to the same scales. The three materials are copper, rubber, and glass. Of course, this will be copper because copper is a metal stress directly proportional to strain. No, this is not copper. Copper will undergo both elastic deformation and plastic deformation before it breaks. This should be glass. 3 should be glass because 3 should be glass. This should be glass because it undergoes only elastic deformation. Then this one, initially it is hard to stretch. It is now easy to stretch. Again, it becomes hard to stretch. This is rubber. That is elastic hysteresis. Initially, Hooke's law is obeyed, and then when the elastic limit is not exceeded, you notice that stress is no longer directly proportional to strain. So this is a ductile material, which is going to be copper. So our answer is going to be 1 is copper, 2 is rubber, and 3 is glass. So the answer is going to be B. The graph is a load extension graph for a wire undergoing elastic deformation. How much work is done on the wire to increase the extension from 10 to 20? So from 10 here to 20, from 10 to 20 millimeters, how much work is done? So this is going to be the area under this graph, which is actually trapezium. This one is in the middle here. The scale on the vertical is 2 divided by 10, which is 0.2. So 1, 2, 3, 4, 5, 6, 7, 8, 9. 9 times 0.2, that is 1.8. Then plus a half, that is 1.9. So in the middle of that box, it will be 1.9. Then here, this is automatically at, this is 1, 2, 3, 4, 5, 6, 7, 8, 9. That is 1.8 plus 2, that is 3.8. Okay, so the work done is going to be the area under that part of the graph, which is a trapezium, and the area of a trapezium is a half into A plus B times height. So I'll just say a half times A, which A is 1.9, plus B, which B is 3.8. Remember, these are masses. So I have to change this to weight. So I will say times 9.81 because the weight is going to be M times G. So 9 times 9.81, that is the force now. Then times the extension, which extension is from 10 to 20, that is 10 millimeters. So that is 10 times 10 power negative 3. I've subtracted 20 minus 10. So I have 0.5 times open brackets 1.9 times 3, plus 3.8, then times 9.81, then times 10 exponent negative 3. So this is giving me 0.279585, which is 0.28. So this is 0.28 joules. So the answer is going to be C. A sample of metal is subject to a force which increases to a maximum value and then decreases back to 0. It increases to a maximum value and then decreases back to 0. The force increases to a maximum value and decreases back to 0. A force extension graph for the sample is shown. When the sample contracts, it follows the same force extension curve as when it was being stretched. So it follows the same force extension curve as when it was being stretched. What is the behavior of the metal between X and Y? Between X and Y. So A is saying both elastic and plastic. So that one is not true. Between X and Y, both elastic and plastic. It can't be both elastic and plastic between X and Y. Then B, not elastic, and not plastic. But when the sample contracts, it follows the same force extension curve as when it was being stretched. That means the extension goes back to 0. Plastic but not elastic. That is not true. If it was plastic, it will it will not follow the same force extension curve because it will retain some energy must be dissipated in the process of removing the load. So it is elastic but not plastic. It is elastic because it follows the same force extension curve as when it was being stretched. It is not plastic because if it follows the same force extension curve, um, it cannot be plastic because if it was to be plastic, then some energy would be dissipated, therefore it would not follow the same force extension curve when the force is removed. So the answer is D. It is elastic but not plastic. I know that is going to be confusing to many of you because they will believe that it is going to be plastic, yet they said uh, when the sample contracts, it follows the same force extension curve. Note that very carefully. The graph shows the length of a spring as it is stretched by an increasing load. What is the spring constant? What is the spring constant? So let's find the spring constant here. So this is 4. The load increases from 0 to 4, and the length increases from 10 to 15. So it means the spring constant by Hooke's law is going to be the difference in the change in the force divided by the change in the length, or divided by the extension. So this is going to be 0.4 minus 0, of course, divided by the change in length, which is 15 to 10, which is going to be 5 times 10 power negative 2. So I'll just say 0.4 divided by 5, 0.4 divided by 5 exponent negative 2, because it was in centimeters. This gives us 8. So the answer here is going to be 8 newtons per meter as the constant. So the answer is going to be A. An elastic material with a Young modulus E is subject to a tensile stress S. Hooke's law is obeyed. Hooke's law is obeyed. What is the expression for the elastic potential energy per unit volume? Okay, so we have earlier on seen that the elastic potential, if I have a graph of stress against strain, for a graph of stress against strain, area under the graph is going to be called the elastic potential energy per unit volume. So area for a graph of stress against strain, area, if we have stress here against strain, we have seen that the area is equal to the elastic potential energy per unit volume. For a graph of stress against strain, we have already seen that area is equal to the elastic potential energy per unit volume. So this area is going to be equal to a half times the stress, which is given as S, then times the strain, which is given as extension over origin length. A half, the area of this graph, area is equal to a half times stress times strain. So this is going to be a half S times E over L naught. And we also know that Young modulus E is going to be equal to the stress over strain, which will be stress S, and strain divided by strain, we get the reciprocal of strain, which will be original length over extension. So the Young modulus is S times original length over extension, so I can make the extension the subject. So this means extension is going to be S times original length divided by Young modulus. So I'm going to go and substitute for extension in that equation. So the area, which is the elastic potential energy per unit volume, is going to be equal to a half times S, where there is small e, I'll put there S, L naught, divided by E. But remember there was L naught in the denominator, so I'll say times 1 over L naught. So L naught has cancelled. So the elastic potential energy per unit volume is now S squared divided by 2E. Therefore, our answer is going to be A. This is going to be the answer. The stress strain graph for a glass rod up to the point at which it breaks is shown. Which statement about the glass rod is correct? Remember, for a glass rod, it undergoes elastic deformation up to the breaking point. Therefore, Hooke's law is obeyed up to the breaking point. So we can say A is saying Hooke's law is obeyed for all values of stress up to the breaking point. That is very correct because it's even a straight line. So the answer is A. A rubber band is stretched by hanging weights on it, and the force extension graph is plotted from the results. What is the best estimate of the strain energy stored in the rubber band when it is extended? So first of all, I will draw a straight line. I'll just come up with some Q shapes. Um, for example, I can take the area up to this point here. You see that area involves this part here, which is not below the curve, yet strain energy is going to be the area under the graph. Energy is going to be the area under the graph. And you notice that the area I've chosen does not include that part. That means the elastic potential energy should be less than the area I'm finding. So it should be less than 30 times 10 power negative 2. Then times on the vertical, this is 15. The scale is 5 divided by 5. That is 1. So 15, 16, 17. So this is going to be times 17. That is the area there. So the elastic potential energy should be less than 30 times 17 exponent negative 2. So the elastic potential energy must be less than 5.1. So this should be elastic potential energy must be less than 5.1. That means this is wrong and this is wrong. Let's also draw another shape here, which is going to be a triangle. I will draw a triangle from the origin. Okay, that is the triangle. So the triangle, you notice that the area of the triangle is less than, because it leaves out this part here and this part here, which means the elastic potential energy should be greater than that area. Let's first find that area. So it will be a half times, the base will be maybe 30 times 10 power negative 2. It is a triangle. And the height will be, let that be 9. So the height will be times 9. So this is times 9. So let's check this. 0.5 times 30 exponent negative 2, then times 9. So this gives us 1.35. So it means the elastic potential energy should be greater than 1.35. So it should be greater than 1.35 or 1.4. So that means these two are still available. Let's now make estimates of this area. So when you look at these two areas, when you look at the area of the triangle here and compare with this area which is remaining, you notice that this area that is remaining is approximately, we can approximate it to half. It is about half of this area which we have obtained. So let's try to check that. So it is approximately half the area at the bottom by looking at this part here and the other part there. So elastic potential energy is going to be approximately 1.35 plus a half of 1.35. This is just an estimate, so let's set that one times 0.5, then plus 1.35. So this is giving us 2.02. So this is very close to 2.02. So the answer is going to be A rather than B. If you want to be more accurate, you can even find the area of one small square and then multiply by the number of full squares and half squares. What do I mean? On the x-axis, one small square is 1 centimeter. Yes, 1 centimeter. On the y-axis, one small square is 1 Newton. So the area of one square is going to be 1 on the vertical times 1 on the horizontal times 10 power negative 2. So this is going to be joules. So one small square represents energy, which is 1 times 10 power negative 2 joules. So you can count the full squares: 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. Here they are over. 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31, 32. Approximately 32. So the area for full squares, so I will say 32 times 1 times 10 power negative 2. That is the area for full squares, plus area for half a square. I'll count the number of half squares. So this is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31, 32, 33, 34, 35, 36, 37, 38, 39, 40, 41, 42, 43, 44, 45, 46, 47, 48, 49, 50, 51. Approximately 50, I'll just say times 50. I'm multiplying by half because they are not full squares, then times 1 times 10 power negative 2. So what is the total area of the small squares? So we have 32 plus 25. 32 plus 20, 32 plus 25 times 1 exponent negative 2. So this is giving me 0.58. So imagine on the triangle at the bottom, whose area was representing 1.35 joules, you add 0.57 joules. So plus 0.57 joules. So you have 1.35 plus 0.57, which gives us approximately 1.9. So the best estimate is very close to 1.8. Note how I got the energy here by counting the number of squares and multiplying by the energy of the area of one small square in terms of joules. What is meant by ultimate tensile stress? I think we have already seen this. The maximum stress a material can withstand before it breaks. Let's see the options which are available. The maximum force that can be applied to a bar of the material before it bends. The maximum interatomic force. It is not interatomic force. The maximum stretching force per unit cross-sectional area. Remember, this is going to be stress before the material breaks. So the answer is C. The maximum stress a material can withstand before it breaks. That is the ultimate tensile stress. The graph shows the behavior of a sample of a metal when it is stretched and until it starts to undergo plastic deformation. What is the total work done in stretching the sample from 0 to 12 millimeters? Extension. Simplify the calculation by treating the curve xy as a straight line. So we are treating this as a straight line. Okay, so I'm just going to find the area. So the work done is going to be called the area under the graph, which will be, for the first part is a triangle, which is a half, times, let's say the base is 10, times 10 power negative 3. Let's say the height is 500 for the first part, plus this other part is a trapezium. So this will be also a half. A for a trapezium can be 500, then B for the trapezium can be plus 550. Remember, the area of a trapezium is a half into A plus B times H. So times 550, then times height, which will be this distance here, which is between 10 and 12, which is going to be times 2 times 10 power negative 3. So let's find the total. The first part is 0.5 times 10 exponent negative 3 times 500, which is 2.5. The second part is 0.5 times 500 plus 550 then times 2 exponent negative 3. That is giving us 1.05. So we can add plus 2.5, which is giving us 3.55. So our answer is going to be B. That is 3.55 joules. Two springs, one with the spring constant K1 equals to 4 kilonewtons per meter, and the other with the spring constant K2, 2 kilonewtons per meter, are connected as shown. What is the total extension of the spring when supporting a load of 80 newtons? If they support a load of 80 newtons, this extension here will be K. Remember, by Hooke's law, the force is equal to K times extension. So extension here is going to be the load, which is 80 divided by, I'll not change the units. I'll just say, okay, I'll change the units, no problem. 80 divided by K, which is 4,000. The answers are in centimeters, so I'll just multiply this by 100 to change it to centimeters. I think this is 2 centimeters. 800 divided by 8,000 divided by 4,000, that is 2 centimeters. Then extension here is going to be equal to the load, which is 80. The constant is 2,000. I'll multiply by 100 to change the answer in centimeters. 8,000 by 2,000, I think that is 4 centimeters. Since they are in series, total extension is the sum of the two, which is 2 plus 4, which is going to give us 6 centimeters. So our answer is going to be C. What is the unit of the Young modulus? Remember, Young modulus is stress. Young modulus is stress over strain, where stress is force over area. Then times, we get the reciprocal, original length over extension. These ones have no units. Force is in newtons, area is in meters squared, so it is newtons per meter squared. So the answer is C. A rubber cord hangs from a rigid support. A weight attached to its lower end is gradually increased from 0 and then gradually reduced to 0. Increased to 0, gradually reduced to 0. The force extension curve for contraction is below the force extension curve for stretching. So down here is contraction, the other one is stretching. What does the shaded area between the curves represent? The total area under the stretching curve is the work done in stretching. Total area below the contraction curve is the area that the work which is returned. That means the difference in those two is the energy which is wasted as heat. So the answer is going to be A. The amount of elastic energy stored in the rubber. The amount of thermal energy dissipated in the rubber. The work done on the rubber cord during the stretching. The work done by the rubber cord during the contraction. So this one is wrong, this one is wrong. The amount of thermal energy dissipated in the rubber, the answer is going to be B. Let me read it again. The force extension curve for contraction is below the force extension curve for stretching. What does the shaded area between the curves represent? The amount of elastic energy stored in the rubber. That is wrong. The answer is B. The amount of thermal energy dissipated in the rubber, that is going to be the area in that part, because that is the energy which is not returned. Okay. The diagram shows a crane on a construction site lifting a cube loaded. A model of the crane, a model is made of the crane, its load, and the cable supporting the load. The material used for each part of the model is the same as that in the full-size crane, cable, and load. The model is, so it means the Young modulus is going to be, the Young modulus is actually going to be the same. The model is 1/10 full size in all linear dimensions, that is diameter, cross-sectional area. Therefore, it is also full dimensions in extension, origin length. What is the ratio stress in the cable on the full size crane over stress in the cable on the model? So remember, Young modulus is going to be stress over strain, where strain is going to be original length over extension. And they told us that the model is 1/10 full size in linear dimensions. So let this be the original for the large crane. Then for the model extension, Young modulus is going to be stress times. Now, because this is reciprocal, I'll just multiply. They say the model is 1/10 full size in all linear dimensions. So this will be times 1/10. This part here will be simply times 1/10 for the model. And if this part is, let's say, 1, the other one is 1/10, it means when you combine these two equations, it means the strain, or when you divide the two equations, or I can say 1/10 times L naught over E, because it's 1/10 of all the dimensions. So if I make, if this is stress of the large crane, this is stress of the model. So I want a ratio of the stress in the cable on the full size crane over the stress in the cable on the model crane. Now note that the Young modulus is the same because the material used is the same for each part. So you can equate the two equations and say, okay, stress for the large crane or the full size crane times L naught over E is going to be stress for the model times it's going to be equal to the stress for the model, stress in the cable on the full size crane over stress in the cable on the model. So we want to find stress. Okay, this is supposed to be 10. So if the model is 1/10 full size in all linear dimensions, so I'll put the model is 1/10. The model is 1/10 full size in all linear dimensions. So if for the full size, Young modulus is stress times original length over extension E. Then for the model, Young modulus is going to be stress of the model times 1/10. Because we got the reciprocal, let this be 10. So this is going to be, when I multiply 10 by this, I get back the original full size. So this is going to be 10. When I multiply for the model by 10, I get the full size. So now let me equate the equations. So stress of the large scale or full size scale times L naught over E should be equal to stress for the model times 10 into L naught over E. So this one has cancelled. So it means stress for the large scale over stress for the model should be equal to 10. So it means the ratio here is going to be 10. So the answer is going to be automatically, this will be A. Is it A? What is the ratio stress in the cable on the full size crane over stress 10 power 0 is 1. No, this cannot be 10 power 0. Sorry, this is supposed to be 10 power 1, not 10 power 0. So this is going to be, actually, this is going to be 10 power, I think that is 10 power 1. I think we have answered a similar question earlier on before. Okay, the stress strain graphs for 4 different materials are shown below. Which diagram shows us the stress? Which diagram shows the stress strain graph for a ductile material? Remember, for ductile material, it undergoes both elastic deformation and plastic deformation before it breaks. So which diagram shows the stress strain graph for a ductile, no, yes, a ductile material undergoes both elastic deformation and plastic deformation before it breaks. So the stress strain graphs for 4 different materials are shown below. Which diagram shows the stress strain graph for a ductile material? So here it is showing, I think here this is automatically wrong. This is actually rubber. This one is actually going to be, I think this is glass. Because for ductile material, it should undergo both elastic deformation and plastic deformation before it breaks. So I think the answer is going to be A. Because here it is initially a straight line. Then as when the elastic limit is not exceeded, then we see that plastic deformation is occurring. Yet here, this is showing that it's a straight line perhaps up to the breaking point, and this is the behavior of brittle materials such as glass. So the answer is going to be A. A number of identical springs, each having the same spring constant, are joined in 4 arrangements. A different load is applied to each arrangement. Which arrangement has the largest extension? We have seen similar questions. These are in series. Total extension is just going to be twice E. These are also in series, so this is going to be 3E. When springs are joined in parallel, the extension reduces, so this will be a half E because each extends by E. Now, if they are used together, the extension will be a half E, and this will also be a third of E. But then we must also look at the loads which have been applied there. We must look at the loads which have been applied there. These values apply when we are applying the same load on the springs. But note that here we are not applying the same load. So if you are very good at dealing with the constants, you will notice that when springs are in series, their total constant can be obtained from the reciprocals. So here, the total constant here can be obtained from 1 over 2 times the constant of just 1. This will be the total constant. And if a load of 2 Newton is applied, then it means total extension. Remember, total extension is going to be the load over the constant, total constant. So total extension is going to be 2 divided by a half k, which becomes 2 divided by a half k, which becomes 4 times k. So total extension here will be 4 times k. The springs, remember, they are identical. They have the same constant. Here we have a 3. That means total constant here is going to be 1 over 3k. So it means if I find the total extension, ignore this because this will apply when they have the same load. If total constant here is 1 over 3k, then total extension here is going to be the load, which is 1 Newton divided by total constant, which is 1 over 3k. Sorry, this is not 1 over 3k. Here I divided, k is in the denominator, so sorry about this. Because total constant is a half k, so when I divide, the 2 goes up, k remains in the denominator, so it is 4 over k. So here is also going to be 3 over k. This is 3 over k. Then here, the total extension is going to be, the constant here is going to be twice k. So total extension here is going to be equal to, did I get the reciprocal right here? 1 over, here total constant is going to be a third of k. Okay, so here it is going to be 6 divided by 2k, which is giving us 3 over k as total extension here. Then here I'm having this will be K and K and K, that will be 3K. Extension is going to be equal to force, which is 8 divided by 3K, which is going to be, what is that value? 8 divided by 3, that is 2.6. So this one is 2.6K or 2.7 divided by K. So let's come and check here. If springs are in a series, total constant is obtained from the reciprocals. If springs are in series, total extension is got from the reciprocals. So here I got 1 over 3, 1 over K plus 1 over K, 1 over K plus 1 over K plus 1 over K, which gave me 3 over K, which when I get the reciprocal, it is K over 3. I think that one I did it correctly. So that is the total constant, K over 3. Then extension is going to be the load over total constant, that is 3 over K. Then here, total constant is 2K. 6 divided by total constant, this is also 3 over 2K. Now the question is, which arrangement has the largest extension? Which arrangement has the largest extension? Because here, the extension here is 3 over 2, 3 over K, and even here it is 3 over K. Let's see here. Here it is 4 over K. So my calculation is showing that the largest extension is actually going to be got from A. The largest extension is going to be got from A because a different load is applied to each arrangement. And we notice that the total constant can be obtained from the reciprocals. And here in the first case, we got 2 divided by a half of K, so the 2 goes up, so it becomes 4 over K. And here we are having 1 divided by a third K, which gives us a total extension as 3 over K. This one is also 3 over K. So me, I'm choosing the answer to be A. Which graph represents the force extension relationship for a rubber band that is stretched almost to its breaking point? Almost to its breaking point. So a rubber band stretched almost to its breaking point. So here, this is not going to be rubber band because we are seeing that as force increases, extension is perfectly directly proportion to extension. Here, this one is a ductile material. Rubber band shows hysteresis. Here, it is almost the same. It is showing that the material is now initially Hooke's law is obeyed, then it is no longer obeyed, and then when there is no change in force, there is an extension that is automatically wrong. Then here is showing that initially the force is directly proportional to extension, then the change in force, there is a smaller change, or there is a change in extension when there is a smaller change in force. But the answer is going to be A because which graph represents the force extension relationship of rubber band that is stretched almost to its breaking point? Almost to its breaking point. This graph shows it has reached a point where there is no further extension. That means as force increases, the change in extension becomes smaller. That means if we continue increasing the force, the only option that is present is going to be the rubber band to break. So the answer is going to be A. A spring is stretched over a range within which elastic deformation occurs. Its spring constant is 3 newtons per centimeter. Which law for the static applied force gives the corrected tension and strain energy? So we know that force is equal to K times X. We know that elastic potential energy is equal to a half times K times X squared. So for the force, we have to check the force and maybe the extension, the elastic potential energy. Let's check the first one. If K equals to 3 over 1, if K equals 3 over 1, then we can check that one. If K is 3 over 1, K equals to 3 over 1 times 10 power negative 2. Then the energy is going to be a half times 3 over 1 times 10 power negative 2. Then we multiply this by extension, which we have taken as 1 times 10 power negative 2. And this gives us a 1.5 joules. So the answer is automatically A without even checking others. Which properties best describe modeling clay? Of course, modeling clay must be brittle. It undergoes modeling clay must be brittle. Oh, modeling clay, not clay, but modeling clay, the one we use in the laboratory. So brittle and ductile. Brittle and ductile. It doesn't break, it's just like that. Ductile and elastic. Elastic means it goes back to its original length. I don't think it normally goes back when the load is removed. It remains. Elastic and plastic. Elastic means it goes back to its original length when the load is removed, but it retains its new length. However, it can be molded into any shape. Therefore, it is plastic and ductile. Although this question here, materials is out of the syllabus, but just it doesn't do you any harm to know that it's plastic and ductile. A steel spring has spring constant 150 newtons per meter. When a 25 Newton weight is hung from the spring, it has a stretched length of 55 centimeters. What was the original length of the spring? So we know by Hooke's law force is equal to K times X. The force is 25. The constant is 150. And the extension is a new length minus original length. It has a stretched length of 55 centimeters. So I'll say 55 centimeters. I think 55 centimeters is going to be 0.55 in meters. 0.55 in meters minus the original length. Let me call it L naught. So what is the original length? So we want to find the original length. So we are solving this equation. So I'll simply say 25 equals to 150 times 0.55 minus 150 L naught. So let's solve this. 25 minus 150 times 0.55 divide by negative 150. This is giving us 0.38. So the original length is 0.38. So the answer is going to be A. A lift is supported by two steel cables, each of length 20 meters. Each of the cables consists of 100 parallel steel wires. Each wire of cross-sectional area 3.2 times 10 power 6 meters squared. The Young modulus of steel is 2.1 times 10 power 11. What distance does the lift move downward when a man of mass 70 kilograms steps into it? Okay, so let's think carefully. A lift is supported by two steel cables, so it means like we have two cables in parallel. And remember, when materials are in parallel, the total extension which they have, the extension of both is half the extension which one material would have. But remember, each of these has 100 cables. So it's like having 200 steel wires in parallel. It's like having 200 steel wires in parallel. That means their total extension is going to be 1 over 200 times the extension of just one wire. So let's find the extension of one wire. So extension, I'm finding E for one wire, E for one wire. Extension for one wire, I will get it from Young Modulus. Remember, Young Modulus is FL naught over AE. So E for one wire is going to be equal to the force, original length, cross-sectional area, then times the Young Modulus. I made E the subject because we have been using this formula many times. So let's substitute. We are finding extension of if the wire was used alone. So this is going to be the load, which is, what's the load? The load is mass 70 times 9.81. Original length of one wire is 20 meters. Divide by the cross-sectional area, which is 3.2 times 10 power negative 6. Then times the Young modulus, which is 2.1 times 10 power 11. So let's find that for one wire. That is going to be 70 times 9.81 times 20. Divide by open brackets 3.2 exponent negative 6. I will again divide by 2.1 exponent 11. So this is giving me for one wire, it is giving me 0.020 meters for one wire. But now note that there now are 200 wires which are acting to be in parallel. So the total extension is going to be 1 over 200 times the extension of just one, which is 0.020. So that is divide by 200, which is going to be, this is in millimeters, so I'll just multiply this by, this is in meters, I'll multiply it by sorry, I was supposed to multiply it by 1,000, which is 0.1. Okay, so I'll multiply this by 1,000, so that is 0.1. So 0.02 times 1,000, sorry, 0.02 times 1,000 to change it to millimeters, then divide by 200, which is 0.1. So our answer here is going to be 0.1 millimeters. So if they are used together, each cable has 100 and there are two cables. So it means total number of wires is 200 and they are behaving as if they're in parallel. And we said if we use materials in parallel, their total extension becomes smaller. If we had two wires in parallel, the total extension would be a half that of one. Now we have 200 wires. That's why I've divided by 200 here. So our answer is going to be C. What is equal to the Young modulus of a material that is extended elastically within the limit of proportionality? So we have area under the force extension graph. That one gives us elastic potential energy. We have area under the stress strain graph. Area under the stress strain graph gives us elastic potential energy per unit volume. The gradient of the force extension graph, that gives us a spring constant or constant. The gradient of the stress strain graph, this gives us Young modulus. Which property of a metal wire depends on its Young modulus? Ductility, elastic limit, ultimate tensile stress. The answer is going to be the spring constant. Why? You can look at Young modulus as F over cross-sectional area times original length over extension, and the force is equal to K times X. So it means the Young modulus, the spring constant of the material is going to be dependent on the Young modulus, K. What is represented by the gradient of a graph of force against extension? Force on the vertical, extension on the horizontal. Force on the vertical, extension on the horizontal. I think that is still spring constant. The graph is, because here we know that force is equal to K times X. So force against X is constant K. The graph is a force extension graph for a wire that is being stretched. How much work needs to be done by the tensile force to two significant figures to cause an extension of 7 millimeters? So we want the extension to be 7 millimeters. Let me look for 7. So this is 5, 1, 2, 3. The scale on the x-axis is 5 divided by 10, which is 0.5. So this is 6. 7 is here. So 7 is here. So remember, the work done must be equal to the work done is going to be equal to the area under that part of the graph. So first of all, we can see that the work done must be less than the total area. If I take 7 times 25, it should be less than 25 times 7 times 10 power negative 3. The work done should be less than that. So I'm saying work done should be less than 25 times 7 exponent negative 3. So the work done should be less than 0.18. So it means these two are out because they are greater. Then the work done should also be greater than the triangle which I'm going to draw in here. So let me draw a triangle here so that I find its area. Oh, I would have drawn a trapezium is not possible. Oh, it is very possible, but it will cause me problems. The work done should be greater than a half times the base, which is 7, times 10 power negative 3, times the height, which is 25. That is the area of a triangle. So 0.5 times 7 exponent negative 3 times 25. So the work done should be greater than 0.088. So work done should be greater than 0.088. So I don't even need to calculate again. It should be greater than this. So the answer is going to be B. The answer is going to be B. The work done should be greater than 0.88 joules. It should be less than 0.18 joules. So the answer is going to be B. I've just used the simple elimination method. The wire stretches 8 millimeters under a load of 60 newtons. A second wire of the same material, that means same Young modulus, with half the diameter and a quarter of the original length of the wire of the first wire is stretched by the same load. Assume that Hooke's law is obeyed. What is the extension of this wire? So since it is from the same material, we know that Young modulus is going to be force over cross-sectional area, the dimension diameter, okay, so it will be 4 over 4f over pi d squared, then times original length over extension. So since the Young modulus is the same, I'm just going to equate two equations. So for the first wire, the force is it is the same load. The second wire, half diameter, is stretched by the same load, so it is going to be 4f. Let the original length of the first wire be L naught divided by pi with half diameter and a quarter of the original length. So let the first diameter be d squared. The extension of this wire, let it be E1 for the first wire. This should be equal to the second wire force, the same load. The original length, the length is a quarter, so this is going to be 1 over 4 of L naught divided by pi. Then the diameter of the second wire is half that of the first wire. So this is going to be a half d squared. Then let the extension be E2. The extension of the first wire, remember, it is 80 millimeters. The load is the same, so I don't need to add it there. So some of these things are cancelling out. 4L naught, 4FL naught have cancelled. Pi has cancelled. So I am remaining with 1 over d squared times E1 is going to be equal to 1 over 4. The 4 here has gone up. So the 4 here has gone up. Okay, maybe times a quarter d squared, then times E2. So this 4 has cancelled, d squared has cancelled. So you notice that 1 over E1 is the same as 1 over E2, which means that E2 and E1 are the same, which is going to be 80 millimeters. So our answer is going to be C. A trolley is held at rest between two steel springs. Each spring has an unstretched length of 0.1 meters. Spring P has spring constant 60 newtons per meter. Spring Q has spring constant 120 newtons per meter. Spring P has extension of 0.4. What is the extension of the spring Q? So let us assume they are applied there. When you compress, or they are under the same tension, P and Q are under the same tension, but remember one has stretched, probably the other one has maybe also stretched. So if the tension is the same, let's say tension in P is the same as tension in Q. If tension in P is the same as tension in Q, then the constant of P times the extension of P should be the same as the constant of Q times the extension of Q. So I'll simply say 60 times extension of Q of P, which is 0.4, should be the same as the constant of the other one is 120 times the extension, which is going to be E times Q. So let's find, EQ, E subscript Q. Let's find EQ. So EQ is going to be 60 times 0.4 divided by 120, which is 1 over 5, that is 0.2. So extension of Q is going to be 0.2 meters. So the answer is going to be B. A lift is supported by two cables, each of length 10 meters and diameter 0.5 centimeters. The lift drops 1 millimeter when a man of mass 80 kilograms steps into the lift. What is the best estimate of the value of the Young modulus of the steel? So a lift is made of two cables. So I'll just find E for one. E for one cable. Extension for one cable is going to be, because when there are two, it drops by one. So for one cable, it is going to be 2 times 1, which is going to be 2 millimeters if it was one cable. So the Young modulus is going to be the load or force over times times 4 pi d squared times original length over extension. So the Young modulus is going to be 4 times the load, which is 80 times 9.81, because they gave us only the mass. Then times the original length, which is times 10, divided by pi. The diameter is 0.5, so I've said 0.5 times 10 power negative 2, but this is squared, times the extension for 1, which is 2 times 10 power negative 3. So this is going to be 4 times 80 times 9.81 times 10. Divide by open brackets, I'll have pi into 0.5 exponent negative 2, then times 2 exponent negative 3. So I'm finding, did I press this correctly? 4 times 80 times 9.81 times 10 divided by pi into 0.5 exponent negative 2, but this is squared. Let me first divide by this. Again, divide this by 2 exponent negative 3. So I'm getting 1.998, which is approximately 2.0, or 2.0 times 10 power 11. So the answer is going to be C. 3 springs are arranged vertically as shown. Springs P and Q are identical and have spring constant K. So if these ones have spring constant each K, remember if one spring is used there, one spring there is going to give us K times E, that is the load. If load W was put on one spring, that means one spring has extension, which is the load over constant K for one spring. Now these ones are identical, their total extension here is a half E. This one, the spring constant is 3K. That means it extends by 1/3E. Remember we said if I know the coefficient of total spring constant, then I get the reciprocal of that coefficient to get total extension for that particular spring. So this spring, which has spring constant 3K, will therefore stretch by 1/3 E. These two springs here have total constant 2K. That's why they are stretching by 1/2 E. We get the reciprocal of the coefficient of this total constant. So it means total extension is going to be 1/2 E plus 1/3E, which is giving us LCM is 6, that is 3, plus 2, that is 5E. But remember, E is W/K. So total constant is going to be 5/6 times W/K. I mean total extension. So the answer is going to be, I think we have done this question earlier on. The diagram shows the stress-strain graph for two wires, X and Y, of different materials up to their breaking points. Both wires have the same initial dimensions. Which statement is not correct? Material X extends elastically. That is true. It extends elastically. Material X extends more than material Y when loaded with the same force. Material X extends more than material Y when loaded with the same force. Let's check. For the same force, remember force is on the vertical because stress is force over cross-sectional area. So it means for the same force, you notice that material Y has a greater extension. For the same force, material Y has a greater extension than material X. So this one is not correct. Because strain is extension over original length. It means extension is on the x-axis. So for the same load F, the extension for X is here, the extension for Y will be around there. So the answer is B. It is not correct. A steel wire and a brass wire are joined end to end and are hung vertically with the steel wire attached to a point on the ceiling. The steel wire is twice as long as the brass wire and has half the diameter. A large mass is hung from the end of the brass wire so that both wires are stretched elastically. The Young modulus of steel is given as that, and of brass is given as that. What is the ratio of the extension of the steel to the extension of brass? So a steel wire and a brass wire are joined end to end. So we have two wires here that have been joined end to end. So we have steel, extension of steel, extension of brass. The steel wire is twice as long as the brass wire. So remember, Young modulus is equal to stress over strain, which is going to be the dimension diameter. Okay, so it will be 4F over pi d squared, then times original length over extension. So that's the Young modulus. We are going to find two equations. So Young modulus for steel is given by that. So for steel is going to be 2.0 times 10 power 11 is going to be equal to 4 times, because they are hung side by side. I mean, they are joined together. The load is the same. So I'll say 4 times F. They said the steel wire is twice as long. So the length here we just say twice L naught divide by pi, and has half the diameter. So this will be a half D squared. Then times the extension of steel, which I'm going to call ES. Then for brass, the Young modulus is 2.0 times, 1.0 times 10 power 11 equals to 4F. The length of brass, let it be L naught because for steel was twice. Divide by pi. If the diameter of steel is a half D, then the diameter of brass should be D squared. Then times the extension of brass, which is EB. So I want the ratio of extension of steel to extension of brass. So I'm going to divide the two equations. Second equation by the first equation. So I have 1 times 10 power 11 divided by 2 times 10 power 11 should be equal to When I divide these equations, okay, I have 4f L naught divided by pi d squared times E brass. When I divide, I will get the reciprocal, so the denominator here goes up. So I have pi times 1 over 4 d squared extension of steel divided by 4f times 2 L naught. So I'll use a different color to cross out some things. 4f L naught pi d squared and 10 power 11. So I have that a half is equal to, here we have ES over 4, so the 4 goes down, but there is a 2 there. So I have ES divided by E brass times 4 times 2. So that is, but these 2 can cancel with the other one, the other side. So it means extension of steel over extension of brass is the 4 goes the other side, so it is going to be equal to simply 4 because I cross multiply. So the answer here is going to be B. The diagram shows the force extension graphs for two materials of the same dimensions loaded into fracture. What describes the behavior of the materials? So this is showing both materials are brittle. Brittle materials do not break without undergoing plastic deformation. Both materials obey Hooke's law. They are not straight lines throughout. Both materials are plastic. They may not be necessarily plastic because they undergo both elastic deformation and plastic deformation. Both materials have the same ultimate tensile stress. Okay, let's find here. Let me draw a horizontal line through this. Okay, I'll draw a horizontal line through this and I see if it is the same. Okay, so both materials have the same ultimate tensile stress. Remember, tensile stress is because they had the same dimensions, so we can say they had the same cross-sectional area. And tensile stress is the maximum stress that the material can withstand before it breaks. And maximum stress is force over area. So if they are breaking at the same force, it means they have the same tensile stress, ultimate tensile stress. So the answer is going to be D. Two wires X and Y, are made from different metals and have different dimensions. The Young modulus of wire X is twice that of wire Y. The diameter of wire X is half that of wire Y. Both wires are extended by equal strain, so the strain is the same, and obey Hooke's law. What is the ratio tension in wire X over tension in wire Y? So we know that Young modulus is going to be 4F over cross-sectional area because it is pi d squared over 4. The 4 has gone up, so that is pi d squared. But remember, Young modulus is stress over strain, so I will put strain in the denominator here. So let's start with the first wire. The Young modulus of wire X is twice that of wire Y, so I will start with Y. Let the Young modulus of Y be E. This is going to be 4. And the tension in wire Y, let it be T, Y, divided by pi. The diameter of wire X is half the diameter of wire Y, so let the diameter of wire Y be D squared, then times the epsilon. Then the Young modulus of wire X is twice that of E, so I'll say twice E is equal to 4 times the tension in X divided by pi. The diameter is half, so I'll say a half D, but this is squared, then times the epsilon. So we can now divide because we want tension in X over tension in Y, so I will divide the second equation by the first one. So we have 2E over E is equal to 4TX over a quarter pi d squared times epsilon, then times, I get the reciprocal of this, pi d squared times epsilon divided by 4ty. So pi d squared, 4 has cancelled, E has cancelled, so I have epsilon has also cancelled. So I have 2 times 2 is equal to Tx. The 4 goes up in the denominator, so it is 4 over Ty. So I want Tx over Ty, so you notice that Tx over Ty is going to be 2 divided by 4, which is a half. So our answer here is going to be a half. The Young modulus E can be determined from measurements made when a wire is stretched. Which quantities would be measured in order to determine E? So first of all, to determine E, Young modulus is going to be force over area times original length over extension. Force is going to be mg. Area is going to be, so the 4 goes up, so we have pi d squared times L naught over E. Which quantities are measured? Original length, mass of the stretching load, original length, diameter, extension of the wire. That one, those are 4 quantities. Mass, new length, the new length alone will not help. Mass, original length, yes. Cross-sectional area, we can't measure the cross-sectional area directly. Mass, new length, the new length, when we measure the new length, we shall not be able, but it can still give us Young modulus if we have measured the extension, because we can again find the original length from extension and the new length, but then this is more direct, so the answer is going to be A. The behavior of a wire under tensile stress may be described in terms of the Young modulus of the material of the wire and the force per unit extension K of the wire. For a wire of length L and cross-sectional area A, what is the relation between E and K? So first of all, we know Young modulus is force over area times original length over extension. And from Hooke's law, we also know that F is equal to K times extension. So what the relationship between E and K? So I'll remove F. So E is going to be equal to KE times original length over A times E. So E has cancelled. So it means E is going to be K L naught over A, which means our answer is going to be C. KL naught over A, or KL over A, because they say the original length here was L. So I'll just say KL over A. The diagram shows the structure of a part of a mattress. The manufacturer wants to design a softer mattress, one which will compress more for the same load. Which change will not have the desired effect? Okay, using more layers of springs, that will actually reduce the compression. So this one is out. Using more springs per unit area. If we use more springs per unit area, it is equivalent to having, because which change will not have the desired effect, because the manufacturer wants a mattress which will compress more for the same load. If we use more layers of springs, we'll reduce the compression. If we use more springs, the manufacturer wants to design a softer mattress, one which will compress more for the same load. Using more layers of springs, okay, this one will increase. If we add more springs, more layers, the total compression increases. Using more springs per unit area. Using more springs per unit area, it means we have many springs here. We have many springs in every layer. Of course, this one will reduce the compression. If we have the same area and we have more springs per unit area, it means the compression will reduce. Therefore, this one will not have the desired effect. If we use more springs per unit area, in a small area we have many springs, the compression is smaller. That one is not going to work. Using springs with a smaller constant, those ones stretch easily. Using springs made from wire with a smaller Young modulus, those ones will stretch easily, because Young modulus is directly proportional to that constant. The Young modulus of steel is determined using the length of steel wire and is found to have value E. Another experiment is carried out using a wire of the same steel but half the length and half diameter. So the answer here is going to be B without wasting time, because what value is obtained for the Young modulus in the second wire? It is the same steel. The Young modulus of steel is a constant, so the answer is E. A rubber band is stretched and then relaxed to its original length. The diagram shows the force extension graph for this process. Okay, the diagram shows the force extension graph for this process. As the force is increased, the curve follows the path OPQ to extension E. As the force is removed or reduced, the curve follows the path QRO to return to zero extension. The area labeled X is between curves OPQ and QRO. The area labeled Y is bounded by the curve QRO and the horizontal axis. Which statement about the process is correct? The area of X is the energy which hits the band as it is stretched. The area of X is the energy which hits the band as it is stretched. That is not true. This area represents the energy which is dissipated as thermal energy when the deforming force is removed, so that the material does not return to its. Some energy is dissipated when the deforming force is removed, so that area is what is represented by that. There is no heating when the band is being stretched. So this one is not correct. Area X plus area Y is the minimum energy required to stretch the band to E. Area X and area Y, it is actually the total work done in loading the material. The total area under the graph OPQ with the x-axis is the work done in loading or stretching the band. So the answer is going to be B. Area X plus area Y is the minimum energy required to stretch the band to E. When describing the behavior of a spring, the spring constant is used. Different loads are used to extend a spring by different amounts. To find the spring constant, which quantities are required? To find the spring constant, which quantities are required? Remember, Hooke's law of force is equal to K times extension. So we need the load and extension. So the loads and extension of the spring. So the answer is C. A metal cube of side L is placed in a vise and compressed elastically by two opposing forces F. How will delta L, the amount of compression, relate to L? Let's evaluate this very well. Young modulus is equal to force over area times original length over extension. So if the same load is applied, we can simply leave F out and we say Young modulus is directly proportional to L and inversely proportional to A times E. Remember, cross-sectional area is going to be L times L, which is L squared. And extension is going to be the difference in L, so it is delta L. Therefore, Young modulus is going to be directly proportional to L, but inversely proportional to L squared times delta L. So Young modulus is that. So one L has cancelled, so it means E is inversely proportional to 1 over L times delta L. Remember, the Young modulus is a constant. So if I make delta L the subject, you will notice that delta L is going to be directly proportional to 1 over L times E. And note that E is a constant. E is a constant, which means delta L is just inversely proportional to L. So our answer is going to be B. The graph shows the relationship between stress and strain for three wires of the same linear dimensions, but from different materials. Same linear dimensions, different materials. Which statements are correct? Number one, the extension of P is approximately twice that of Q for the same stress. The extension of P is approximately twice that of Q for the same stress. For the same stress, let's see the same stress. Now the extension of P is twice. It is actually half. The extension is of P is here. The extension of Q is here. Remember, stress is extension of original length, and original length is a constant. So it means the extension of P is a half that of Q. So A is wrong. This one is not correct. I mean, the first statement is not correct. The ratio of Young modulus of P to that of Q is approximately 2. Okay, let's check. Remember, Young modulus is equal to stress over strain. So if I take the same stress, for the same stress, the extension of P is half that of strain. That means, and since Young modulus is inversely proportional to strain, when strain is a half, the Young modulus is twice. So that is correct. The ratio of Young modulus of P to that of Q is twice. So this is correct. For strain less than 0.1, R obeys Hooke's law. Let's check. For strain less than 0.1, somewhere here, it is a straight line. That is very true. Stress is directly proportional to strain. R obey Hooke's law. So this is correct. So the answer is going to be C, 2 and 3 only. We have seen this one. The extension of P was half that of Q. So this was not correct. The graph shows the effect of applying a force of up to 5 newtons to a spring. What is the total increase in length produced by a 7 Newton force? So let's first find the constant. The constant is going to be F over X by Hooke's law. So if F is 5, then extension is 14 and 11, that is 3. I think this is 3 centimeters. So this will be 3 times 10 power negative 2, that is K. Now using Hooke's law again, F is equal to K times X. So F is now 7, K is 5 over 3 times 10 power negative 2, then times X. So I'll press my calculator and find X. 7 times 3 exponent negative 2 divided by 5, which is giving us 0.042. We multiply by 100 to change to centimeters, which is giving us 4.2. So X is equal to 4.2 centimeters. So the answer is going to be A. This was 3 centimeters. The following force extension graphs are drawn to the same scale. Which graph represents the deformed object with the greatest amount of elastic potential energy? Remember, elastic potential energy is going to be the area under these graphs. And elastic potential energy is only got from the straight line part, where Hooke's law is obeyed. So this one, you notice that this area is smaller than this one. I think this area is smaller than this one because it is the area of the triangle below. This area is bigger than A and C. And here we notice that the elastic potential energy, remember, is going to be the area under the graph. Precisely, this is the answer because this is going to be the greatest area. And if we are getting elastic potential energy, we look for that part where Hooke's law is always obeyed, or the energy which can be returned. Okay. In stress-strain experiments on metal wires, the stress axis is often marked in units of 10 power 8 pascals, and the strain axis is marked as a percentage. This is shown for a particular wire in the diagram. What is Young modulus? So Young modulus is going to be stress divided by strain. So stress is going to be 3 times 10 power 8. Strain is 5%, which is 0. I'll just say 5 over 100. So 3 exponent 8 divided by 5 over 100. What have I said? 3 exponent 8 divided by 5 over 100 is 0.05. So this is giving us 6 times 10 power 1, 2, 3, 4, 5, 6, 7, 8, 9. So it is 6 times 10 power 9 pascals. So the answer is going to be D. A spring is compressed by a force that by a force. The graph shows the compression force F plotted against the length L. The graph shows the compression force F plotted against the length L of the spring. What is the spring constant of the spring? So let's find the spring constant. Okay, so what is the spring constant? So to find K, we need the load, or the difference in the change in the load over the change in the length L. So K, the change in the load is 12. Then the length is from 40 to 100, that is 60 millimeters. So that is 60 times 10 power negative 3. So 60 times 10 power negative 3. So let's say 12 divided by 60 exponent negative 3. So this is giving us 200. So the constant here is 200 newtons per meter. So the answer is going to be D. Lastly, in this part, in part 3, a ball is thrown horizontally in still air from the top of a very tall building. The ball is affected by air resistance. Of course, this is a question of kinematics. It is just a stray question. What happens to the horizontal and vertical components of the ball's velocity? Remember, the vertical component of velocity is always constant. Reason, there is no resultant force in the horizontal. Sorry, the horizontal component, not the vertical component. The horizontal component, which I'm calling V in the X, is always constant because there is no resultant force in the horizontal. So the horizontal component should remain constant. So decreases, that is wrong. The horizontal component of velocity does not change. A ball is thrown horizontal. A ball is thrown horizontally in air. There is air, so this is not true. This one, what I've mentioned, only applies for projectiles where air resistance is negligible, so this is not true. The ball is thrown horizontally in air from the top of a building, so it is thrown horizontally in air from the top of building. So if it is thrown in air, if it is moving in that direction, then air resistance is in the opposite direction. That means now V in the X decreases. The horizontal component decreases. It does not remain constant. So C and D are wrong. If there is air resistance, which acts in the horizontal, in still air from the top, then of course, as it is falling due to gravity, it means it's going to be falling downward. It will fall downwards to follow such a path, a parabolic path, or such a path. The velocity in the horizontal decreases. And how about the velocity in the vertical? Of course, the velocity in the vertical, because the ball is affected by air resistance. So the velocity in the vertical is going to be affected. Of course, it is going to be increasing. So A is saying increases at a constant rate, and B is saying increases to a constant value. That is very true. If air resistance now changes direction because the ball will be falling downwards, air resistance is upwards, it increases to a constant value. That means it goes to a terminal velocity. So we reach terminal. We call it terminal velocity. So it increases to a constant value, not at a constant rate, but it increases to a constant value. At that constant value, the acceleration becomes 0. So the answer is going to be B. I think let part 3 stop there. Part 4 will be the last one, and it will be very short. I hope you learned a few things from here. In case I made some mistakes, I'm bound to make mistakes. You can always write to me and correct me. I'm very ready to always rectify errors. Nevertheless, I've tried my level best, and I wish you the best. Bye bye.